before I begin, I just wanted to give a shout out to my co-authors. Jessica Reimer has helped with various aspects of our projects, collecting data over the years, and she's the one that has been working up the winter bat activity data that I'll present tonight, part of what I'll present tonight. And Tori Rhodes has been my colleague working on the bats since, what was it, 2017? 2016. And she just completed, successfully defended her master's thesis.
Oh, congratulations! Yay! And she gave a program for us recently too. That was fantastic. So, yeah.
Her expertise goes far beyond bats, but yeah, she did a master's using I'm using scent dogs to locate hibernacula. It was a really challenging project, and she did just an amazing job. So, thank you, Tori. So tonight I'll be talking about various aspects of bats in winter. So why we've been studying bats in winter, bats in the Southeast Alaska, they spend more time in hibernation than they do out of it. It's a really critical time for bats. And it's also one of the areas that we have so little knowledge. There's just still so many questions. And when we first started this research, we really knew almost nothing about hibernation in not only just in Alaska, but in the West in general. But it became critical to start learning more with the advent and spread of a disease called white nose syndrome. And it's a fungal disease. I hope you all have heard of it. It's killed millions of bats back east and in the Midwest, and it just continues to spread. And so, we were concerned about our bat populations here and whether they'd be vulnerable to white nose. So most of our bat research has actually focused on bats in winter. And in the wintertime, bats are doing one of two things. They're either flying around on the landscape, which is not what we usually think of, or they are in hibernation. And so I'll start by talking a little bit about winter bat activity, what species we have that are active in winter, where they're active, and the effective temperature on that activity. And then I'll move into hibernation and talk about the work we did locating hibernacula in the Juneau area, look at some of the microclimates in that hibernacula and kind of the implications for where and bats hibernate and the microclimates within there for white nose, and also, if we have time, maybe a little bit for climate change. So yeah, the hibernation season in Southeast Alaska is 6 to 9 months long. Most bats have hibernated by the end of September, and most bats don't really start to emerge. Emergence starts in basically the second week of April most years, but most bats aren't emerging until sometime in early or mid-May. It is the reproductive females that will emerge first. They want to maximize the time that they have. So female bats, they mate in the fall and they store the sperm over the winter. And so when they emerge from hibernation, that's when the egg gets fertilized and gestation begins. So they want to get this process going as soon as possible. And that means they'll have their pups more quickly, and they'll give those pups more time to learn how to fly, learn to become proficient foragers, and be able to put on the fat to survive their first winter. So the males are not under those similar constraints, and some of them won't emerge until sometime in June even. So they may spend 3 months active and the rest of the time in hibernation. So let's talk a little bit about what happens during hibernation. So bats are looking for cold places to hibernate. When it's cold, they're able to drop their body temperature to just a degree or two above the ambient temperature. So during hibernation, they're slowing everything down. So they drop their body temperature. They reduce their heart rate. So their resting heart rate is usually 1 to 200 beats per minute. During hibernation, it will drop to as low as 10 beats per minute. And it's the same thing with their breathing rate. They may take as little as 1 breath an hour during hibernation, which is just crazy when you think about it. So their metabolic rate is also, again, reduced to a fraction of what it is when they're active. And this means they consume far less energy when they're hibernating than when they're active. And so, again, they're looking for cold temperatures. So for little brown bats, if they can hibernate at 2 degrees, that's the optimal temperature for them to minimize the amount of energy they will consume during winter. And most of that energy consumption actually occurs during these periodic arousals. So bats will arouse for a few hours, and they'll do that, periodically. It depends on the species. Little browns tend to arouse about every 3 weeks. These short arousals consume more than 80% of the total energy that bats use during the winter time. So they're energetically very expensive. And so think about that when we're talking about bats not only being awake, but actually flying on the landscape, which is even more energetically expensive. So, all their body systems have slowed way down, and this means that the immune system is also suppressed during this time. And that makes them very vulnerable to things like a fungus that likes to grow on hibernating bats. So these are some bats from a cave in New York. You can see why the disease got the name white nose syndrome. The fungus is visible as a white fuzz on the muzzle of the bats. You can see in the photo on the left, the fungus doesn't just grow on the muzzle, it grows on any exposed membrane, so the wing membranes and forearms, ears. And again, the disease only grows on hibernating bats. Once the bats wake up in the spring and their body temperatures return to normal, they clear the fungus. So they can survive hibernation, they've got a shot. So white nose is transmitted during hibernation, and it's spread in one of 2 ways. Bats can either get it by contacting another bat that has white nose, or from a surface. So if an infected bat, moves from one place to another, and another bat, roosts there, they can pick it up from the cave walls or other surfaces. Now, this fungus grows best at relatively cool temperatures for fungus, so about 55 degrees Fahrenheit, and under high humidity conditions. So this is what it looks like, for bats back in the east. So east of the Rocky Mountains, bats hibernate primarily in caves and mines, and little browns in particular will often hibernate in these huge aggregations, or they used to, and they often clustered, really tightly packed, so some of the aggregations were tens of thousands of bats in these cave and mine systems. So 60% of all the caves where they found bats hibernating had more than 1,000 bats in them. So that's a lot of bats all in one place, all being very cozy with each other, which is why white nose had such a dramatic impact in the East. So there were cave systems where mortality was essentially 100%. And so basically the fungus would arrive in a cave. It would be spread throughout the cave during the first year by bats moving around inside. Every bat by the end of the second year that entered that cave would become infected. And because the fungal spores, remain in the cave at high levels, they got infected early, and the fungus had all winter to grow. And so mortality has just been really, really high. It's a little different than the fungus that causes white nose is actually found in both Europe and Asia. And bats there will develop white nose, but it doesn't kill them. And the reason seems to be that there's something in those hibernation sites that reduces the level of the fungus over the summer. So it's in very low levels, like 1% of what it was in the wintertime in the summer. And so it takes longer for the bats to become infected, and that means the fungus doesn't have as long to grow. And so the loads are lower, and bats tend to survive the infection and clear it once they emerge from hibernation. But here in North America, we really have not seen that, and the spread and devastation has just been horrible. It was first discovered in 2006 in a cave in New York, and you can see here in 2023, it's basically spread almost, it's basically spread to the Rockies. And then unfortunately, in 2016, white-nosed bat was found infected bat was found in Washington State. And so it's believed to be some kind of translocation event, either, the fungus brought in by either a human like a caver or an infected bat, probably more likely an infected bat that hitchhiked a ride in a truck or an airplane or car. Or bats are amazing hitchhikers. One even tried to hitch a ride on a space rocket. And so the disease has shown up in the West earlier than we had hoped. So I'll talk a little bit now about winter bat activity, and I'll start by talking a little bit about why bats might be active in winter. And I mean, the short answer is we really don't know. There's been a number of hypotheses that have been presented. The first being, well, it would make sense that bats would, if they were out in the landscape, would want to try to feed. Now, obviously, in a place like Juneau or places in the far north where there are no insects that are active, that's not a possibility. But further south, in places like western Washington and southern BC, bats have been observed foraging when the weather is milder and the insects are active. Another hypothesis is that bats emerge to drink. So, bats have really large wings, and this means they have a very large surface to volume ratio, and it means they lose both heat and water, through those membranes. And so they dehydrate very easily. And when they're hibernating, they can do some things to minimize that. They can, they fold their wings in so they're not, the surface area is reduced. They may cluster, which also reduces the surface area, and they can choose very humid places to hibernate. So there are some places, like in the prairies, where hibernacula, they're just not very, very moist, and there was some thought that bats were having to emerge in the winter to drink, but doesn't really seem to be the case. And so our colleagues in BC put out a heated water tank outside some known hibernation sites to see if bats would use it. No bat ever came and drank, and they captured some bats in southern BC and offered them water, and most of the bats actually didn't take any. So again, there's not really strong support for that. Roost switching is one of the more promising explanations for a lot of the activity that we see. Those same BC colleagues, and Tori actually helped out on that project. They're very hardcore, and they went out and trapped bats in the wintertime, which that's a cold night, and a lot of nights where you don't catch anything. But they put radio tags on the bats they did catch, and they found that bats were switching roosts relatively frequently. These were California myotis and silver-haired bats, which we have here in Alaska. And there's a number of reasons bats might want to switch roosts. As temperatures and environmental conditions change, the area that they chose, whether they're hibernating, in a rock crevice or under some bark, or the temperatures and the conditions can change and become unsuitable, and so they may need to go find. Sometimes they can move within the hibernaculum, but other times they have to move elsewhere to find better conditions. And then the last hypothesis is mating. Now we know in cave systems that bats will arouse during the winter, and they will mate during the winter. It didn't seem very likely in the West, where bats are not hibernating in caves. However, some of the bats they were capturing in winter showed signs of recent mating activity. And so it may be that, that is also playing a role. So how did we study winter bat activity? We did not spend many cold nights out with empty nets trying to catch bats. we decided to use acoustics instead. So bats will echolocate. It's how they navigate and how they hunt their prey. And with special bat detectors that can detect ultrasound, we can record their calls. And so we had a network of bat detectors that we put out. Now, these are some sonograms. So this just shows the frequency that the bat is echolocating on at. And so, songbirds sing, and you can look at a sonogram of a songbird and tell what species it is. And to a certain extent, you can do that with bats if you get the right call. So they change their call types depending on the situation. So bats are different than birds in that it's a functional, the sound they are producing has a function. And so they are using it to navigate, and they are using it to catch prey. And so that constrains kind of the frequencies that they can use. That depends, and it's also constrained by their environment. So bats will change their call as they approach an insect, or if they're foraging in high clutter conditions, which just means there's a lot of vegetation, just obstacles around. And so there's a lot of calls that cannot be identified to species. And just to give you an example, so we have 5 species of the 6 here in Southeast Alaska that if you get the right kind of call, you can identify to species. But the 6th one, so you can see here, this is a little brown myotis call, and you can see it starts, kind of low sloped and frequencies down below 40K, and then it's approaching some clutter. And so what happens here is the minimum frequency goes up and the calls become much, much straighter. And they resemble those of calls that a long-legged myotis would make. Unfortunately, this is really the only call that the long-legged myotis makes. And so it's basically, you can't tell it apart from a little brown. So if a little brown, you see this kind of call, you know it's a little brown. But if you see this, unless you know the clutter conditions, you can't tell what it is. If it's a low clutter, you would know that that's a long-legged myotis, but otherwise you can't tell those apart. So we surveyed during winter, and bats, there are some bats that are active into November and some bats that emerge as early as March. So we constrained our definition of winter to be just midwinter, essentially December, January, and February. We have surveys from 10 years at 77 different survey sites. Most of these sites were in Juneau. We also had 5 sites in Sitka and some sites elsewhere in Southeast. 3/4 of the sites, we surveyed for at least 3 months, but there were some that were for shorter periods of time. And unfortunately, it's really hard to maintain this equipment in the winter. The batteries go dead really quickly, and it's just kind of a nightmare. So unfortunately, these squares indicate areas where we just had short surveys. So you can see this. Let's go to the next slide. These are the results here. You can see those sites that had just a short surveys tended to not record any bats. That doesn't mean that bats aren't active in winter there. It just means we didn't survey them long enough to determine what was going on. However, we did record over those 10 years over 22,000 bat calls, and we detected 3 different species. We detected California myotis, which had by far and away the most calls. Also silver-haired bats, and also a few little brown bat calls as well. There were 2 species that we did not detect, but again, this doesn't necessarily mean they're not active in winter. The long-eared myotis is known as a whispering bat. It makes a very quiet call, which means you have to be very close to it. It has to fly very close to the detector for it to be picked up. So it's very likely that they could be active. We just don't detect them. And the Yuma myotis, its range is just in this very southeast part of Southeast Alaska. So there was only 1 site that we monitored that had the potential of detecting that, and it didn't. And so about 51% of the calls were not identifiable to species. So this gives you an overall sense of how many bat calls were recorded at each of the sites. And you can see that almost, the overwhelming majority, actually, I think 99% of the calls were in Sitka. But let's take a look here at Juneau first and see what, so this map uses call rate, which instead of the number of calls, because we monitored for different number of nights at all these different sites. So this is just a way of standardizing it, the number of calls per every night that the detector was operational. And so, it ranged everywhere from 0.001 means that on average we got one call every 1,000 nights, all the way up to, we got over 8 calls per night at some of the detectors. And that doesn't mean that every night they got 8 calls. You could get 200 one night and 0 the next, but on average, it's over 8. So you can see here that the 2 most active species were the silver-haired bat and the California myotis, and their distribution of activity was actually pretty similar. So most of the activities, here along Outer Point, and then some scattered activity in the Mendenhall Valley here, their area there, and a couple, here just on the coast there, and this is a site at Eagle River. So the other thing is, almost all the sites that had activity were on the coast or very close to the coast. And so the further you go inland, it seems a little less likely you are to detect bats. And with the exception of that site at Eagle River, which we had some detector data from the fall that suggested there could be hibernation sites nearby, and so that could explain the pattern of activity as well. So in fact, you're most likely to detect bats close to where they're hibernating. So this would suggest that, whatever resources these bats are using for hibernation are really abundant in that Outer Point area. And we did have a radio tagged female in spring who was using, are you familiar with the cliffs out there? So if you go on the Outer Point Trail or the Rainforest Trail and you go right, there's some big cliffs there, and that's where she was roosting. And we don't know if that's where she had spent the winter, but it's possible. And it seemed like a lot of these shore sites did have some kind of rocky feature nearby. And so that's a possibility, is that they're using these rocky outcrops and cliffs and stuff for hibernation, and so that's why we detected them in these areas. And we know this to be true for little browns. Little browns not very active outside of the hibernacula in the winter in the west. So this is very typical for what other studies have found as well. And right here, I've been talking a little bit about where we found bats hibernating. Well, one of our main hibernation sites was right there. So not surprising that when we got little browns, it was close to that site. So what's going on in Sitka? Well, almost all the activity, I think 97% of the activity, was at this one site on Galenkin Island, which is in Sitka Sound. And there are it's a milder climate out there, and there are a fair amount of winter active insects, winter crane flies and other flying insects. So we assumed they were feeding there, and that's why there was so much activity. And that activity extends throughout the night. It's not just like they were roosting there and flying somewhere, just coming out briefly, because the activity was scattered through the entire night. We didn't really see any feeding buzzes in the calls, which is just as a bat approaches an insect, the calls get very steep, very short, very quick. But they're also higher frequency, which means that they aren't, the sound doesn't travel as far. So we're trying to figure out if we can do some comparisons with that area in the summer to see if we detect feeding buzzes in the summer when we know they're feeding, or if they're just kind of dropping out. And there was only a single silver-haired bat call here, and no little browns in Sitka. So, sorry to throw some graphs at you guys. So this orange line indicates activity, number of calls per night, and this is all multiple years of data all meshed into one a graph. So you can see, activity starts up here in May and declines in August. And it's interesting, but the activity pattern at Lincoln Island is kind of the reverse. So as activity is dropping off, at Indian River. So this is a site on Indian River in Totem Park, not far from where the road, Sawmill Creek Road crosses the river. And yeah, that's when activity seems to pick up, and as it dies off on Lincoln Island, in the spring is when we see that increase in Indian River. So it certainly does seem, most of these calls will be California myotis, that there may be some movement, from the Baranof to other islands in Sitka Sound. Sorry to throw yet another graph at you, but this just goes to this. Again, the bars represent the number of bat calls on a given night, and these blue dots show, or the dots show that the detector was operational during that time. And blue dot shows if the temperature was below 41 degrees, and the red dots indicate when the temperatures were above 41 degrees. And so you can see there's a really pretty strong correlation. The Californias really don't like it when the weather is very cold, and they tend to not be very active during those periods, which is interesting, and may have something to do with prey availability. And it's really different from what we saw in terms of temperature for the Juneau area. So here you can see, again, each symbol represents a bat call, and the y-axis, or is the total number of bat calls at that temperature, sorry. And so you can see there's a lot of activity at temperatures above, when the maximum temperature is above freezing, and even more when it's above 5 degrees in Sitka. And in Juneau, yeah, their bats are active at temperatures way below 0. So that's may just reflect, Juneau's a lot colder than Sitka is. And
but your left axis is hugely different, so there's a lot fewer.
Yes,
left
yes,
axis.
yep, that's exactly right. Yeah, again, that 8 calls per night in Sitka versus, much lower rates, usually less than 1 call per night in Juneau. So maybe the temperature is part of the reason why the bats aren't as active in Juneau. And if they're going to be active, they probably have to be willing to be active at colder temperatures. And there's also, some sense that bats do adapt physiologically to kind of the typical conditions in that area. So bats in the prairies, for example, where it's very dry, have much less, they don't dehydrate as easily as bats, forest bats, that live in a much moister climate nearby. And so it could be, bats in Southeast Alaska are some of the most distinct genetically of, they are the most distinct population. And it could be that there's many local, populations that are adapted to those colder or those warmer conditions. And so, they just become adapted to it, and so that's what they do. So to summarize, what we found is activity is largely confined to the coast. We don't find much of any activity inland. The California myotis, which is, interestingly, is the smallest bat. So, it has a high surface to volume ratio, which means it loses heat more quickly. So that's not necessarily something we expected. And silver-haired bats were the next most active. and they were found in similar places to the Californias. And then again, the little brown bats, which is our most common species, almost never detected in the winter. And we only found them near known hibernacula, at least in the Juneau area where most of the calls were recorded. So where do little brown bats in Juneau hibernate? To answer that question, we couldn't use acoustics, or we couldn't just use acoustics, so we had to capture some bats. So to do that, we strung up some mist nets, which are really similar to what they use for birds. We put them across gaps in the vegetation, along known flyways, trails, areas where bats would be present but not expecting something. Once we extract the bats, we would clip some fur between their shoulder blades, and we use surgical glue to attach a tiny little radio transmitter. And so the first year, we tracked every bat, tried to track every bat to its day roost. And we did that day after day, and most of the bats that first year we caught the yellow dot is the pond at Fish Creek, which is where it ended up being our main capture site. Most of the bats we caught there, and most of the bats did roost kind of in that same general area. So we go out and find a bat, and then one day the bat would be gone. And we had no idea where. So we would search around the areas where we'd been finding bats, listen for a signal, and weren't finding them. So I went up in a plane and searched all around, and still had no luck. Once they were gone, they just disappeared. So the following year, we decided to do something a little bit different. And in addition to doing the ground tracking, at sunset, when the weather permitted, I would go up and fly at night. And so the idea was, because bats were roosting mostly around that pond, I would circle around that pond and wait for one to make a move, and then I would follow that bat. And so here is just a little simulation of one of our bats. So he was roosting on River Place, and then when I first located him, he was on the tip of that peninsula in Mendenhall Lake there. And that was a spot where he and a couple other bats had been spending their evenings, so I didn't think anything of it and went off back to Fish Creek to track other bats. And then I got back and he was gone. So we decided to go over by Ock Lake, which is a known foraging area. And there we did end up picking up his signal, and we ended up catching up to him about halfway down the Mendenhall Peninsula. And so we basically just kept circling the area, and I would take GPS points along the way. He essentially followed the shoreline there at the coast. And then, crossed over to North Douglas there. And so it turns out this stretch of North Douglas, a lot of bats do that. So we did these driving surveys in September, and we normally don't find bats, between the boat ramp and Outer Point, and there was a lot of bat activity there. So this seems to be a common route for the bats that are heading off to hibernate that they take. So we went over to Outer Point, which does seem to be some of the bats that we tracked, kind of spent some time there before they went ahead and went across Stevens Passage. And he made landfall over near Bear Creek. And kind of followed the drainage up to the shoulder of that ridge there. And then he basically followed the ridge line. Until he kind of dropped down, followed the drainage down to the base of the ridge on the other side, and essentially, I think the last location.
How long did this take? How long
So,
did you find them?
I think we picked him up at 9 o'clock, and it was 11:30.
Wow.
So
How
he
much
kind of booked. I
distance?
mean, that's
What was the distance?
it's probably close to 30 kilometers. It was a good ways. Yeah, he was
Yes.
flying hard. So we ended up being able to track the flight paths or part of them at least for 5 different bats. And it was interesting, and they did tend to follow the shorelines, also drainages and ridge lines. And then the ones that were crossing over the water a little bit further south took advantage of horse and coal islands, and traveled over those to reduce the time that they had to spend flying over open water. So migratory bats do these same things, but it's been debated, or I guess the evidence has been equivocal for whether hibernating bats that are going shorter distances also follow these landscape features. So it's nice to be able to demonstrate that, at least in some cases, they do. So we ended up successfully locating 10 different hibernacula, and they were 2 types. So we found 2 males using what we call root ball or root wad hibernacula, and it's basically just a hole in the ground beneath the root system of a tree or a stump. And these were typically low elevation, flat forested areas. But the other 8 were in this specific habitat. The European entomologists coined a horrible term for it, the milieu souterrain superficiel, which translates roughly to shallow underground habitat. So I'll call it the MSS from here on out. But it's referring to these spaces between the rocks. So MSS is typically found on steep hillsides where there's a shallow layer of soil and vegetation, and beneath that it's all rocks. And so the bats are just crawling into those spaces between the rocks. And so underneath, all these hibernacula look like that. They look very similar. And I should say, in some ways, these habitats are very similar to caves. So they are permanently dark, they are underground, and they even share some of the same fauna, so some of the same insects and invertebrates and things like that. But they are different mainly in that the spaces are very small. So unless it's a big boulder field, sometimes people can get into spaces between them, but for the most part, the spaces are tiny. And they are also closer to the surface, which means they're more sensitive to external environmental conditions. So they're not as stable as caves. So externally, they all looked a little different. Some of them look like no more than holes in the ground, nothing to mark them whatsoever.
Is that as big as a tennis ball, or how big is that? That hole?
Yeah, about as big as a tennis ball. Yep. The other one on the left is a little bigger, but yes, they're small. Most of them were associated with some kind of rock feature, rocks protruding from above the ground. This was the very first one that we found, and this is just a small little chest-high outcrop, and you can see the actual entrance here. It's just this really narrow little, I don't have anything for size in there, but yeah, like a credit card would be like that big. And we also found a bunch that were associated with much larger outcrops. But again, the interior all look the same, those jumbles of rocks. So this is what the habitat around these looks like. These are really, really steep slopes, and you can see that. You look, all the trees have this kind of J shape at the base. there's some over here, I think, that are, I can't see that. But it's, that's indicative of a hillside that's kind of slowly creeping downward. So, yeah, they're more stable than an avalanche zone, but not as stable as bedrock. And once we found one hibernacula, we would kind of look around the area, and in many cases, we did find other additional sites nearby that were also being used by bats. Just to show you, there's been one other telemetry study of little browns, and this took place in Colorado. And similar, this is also, a type of MSS. It doesn't have that soil and vegetative layer covering it, so those openings are kind of more open to the environment, but it's up near timberline, which means in the winter it's covered with snow. Snow is a fabulous, fabulous insulator. Again, very similar to what we found here. And so one of the interesting things is all 10 of those hibernacula were found on the same two ridge systems. So the one over here by just this ridge right up above the Fish Creek Pond there, and then over on Admiralty where we saw that male that ended up right there. And that includes the root ball ones, so I wouldn't necessarily have thought they'd be associated with the ones on the hillsides, but they seem to be, which is kind of interesting. So, even though we don't have large aggregations of bats in caves, it does seem they are aggregated to a certain extent on these certain kinds of hillsides. And Tori tried valiantly to use scent dogs to find other hillsides where bats might be hibernating. We didn't have any luck, and so we don't know if we just, weren't able to search the right places, or if, we don't really understand what they're selecting for, what makes this a good hillside and a different one isn't a good hillside. So there's still lots of questions. So once we found these, we used these tiny little I-button data loggers, which we stuffed into the holes as deep as we could reach them, which ended up being about 3 feet max. Just the way the rocks are arranged, it was just really hard to poke something in there. And this is just an example of, at one of the sites, this is that first site that we found. Sorry for another graph. This shows relative humidity up here, and the dark red means what it was like inside the hole, and the lighter color is what the ambient relative humidity was like. So you can see these sites are saturated. They all look like this. They were all 100% humidity all winter long. And you can see that temperature does vary, but it's much more stable than the outside temperatures. And the deeper you go, the more stable and the warmer it gets. We don't know how deep the bats are hibernating. The MSS it's just really hard to get in there. And so there really isn't the technology available, yet to be able to investigate further. So the bats are not visible from the surface. We did try using one of those snake cameras to look for them, but again, we could only get it in about 3 feet, and so the bats must be hibernating deeper than that. So I mentioned about white nose and how devastating it's been for bats in the east that hibernate in large numbers in caves. So what do we think might happen as white nose moves west? So this change in hibernation strategy from large groups of bats, and they're traveling longer distances. So our bats stayed home, basically. They hibernated locally. The furthest distance, straight line distance that we got was 24 kilometers. Now the bats back east, caves are a more limited resource. They're flying much longer distances, tens or even hundreds of kilometers to get to these places. So they're moving around, a lot more. So what we're hoping is, and which does seem to be the case when we look at some maps later, is that this will slow the rate of spread. The fact that the bats are not moving long distances means it will take longer for white nose, even if it did reach Juneau, to then get to Chichagof and Sitka, and just because the bats are are much more localized. The hibernacula, of course, are much smaller, with far fewer bats. I think the most we've used trail cams to look at bats entering hibernacula, and most that we've detected have been, I think, 12. So versus thousands of bats in those caves. And so that should, reduce the opportunities for transmitting the virus, the fungus. And they're also cold. So the temperatures that we found were right around 0 degrees, and probably a little bit warmer where the bats are. But these temperatures are much, much colder than back east, where they're much more typically like 4 to 7 degrees Celsius. Sorry, I don't know what that is. So like in the 40s and 50s, I think, low 50s. So the fungus should grow much more slowly. Again, the optimal temperature for it to grow is 13 degrees. So the warmer the hibernacula, the faster it's going to grow. However, it also does grow better in humid conditions. And so the thought was that because our hibernacula are very, very wet, that this would promote fungal growth and could potentially be a problem. However, it turns out more recent work has shown that bats actually survive better in cold and wet conditions than they do in cold and dry. And that's because the fungus needs moisture, and to get it, it goes deeper into the tissues of the bat. So it actually is much more invasive and damaging to the bat in cold and dry conditions. So all this, I think, is really good news for bats in the Southeast and in the West in general. That white nose should not have the same devastating effects that it has had back east. And I think you can see it when you look at this map here. So this shows how far the fungus had spread in the 5 years since it was first detected in the east versus when it was first detected in Washington. And so you can see it's not spreading anywhere near as quickly. The mortality also has not been as dramatic. So I think it was 2022 where they've had the first reports of maternity colonies, kind of mass or dramatic declines in the number of bats at some known maternity colonies within 40 kilometers of where that first white nose positive bat was found. So yes, there will be some declines, but again, that's 5 years after we've got declines that are not 100% and still confined to a very small area. So I think the news, is good for Western bats in general and our Alaskan bats in particular. And I don't know, do I have time? I'm over time already, so I'll skip the more graphs. So a ton of people helped contribute to this project, and I want to give a shout out to Glenn Bayless, who helped us with some captures and has helped us with some acoustic monitoring as well. So thank you. I'll take any questions.